Hi everyone, I am Ramin Raziperchikolaei and this is a joint work with my colleagues at Rakuten. In this presentation, I want to talk about neural representations in hybrid recommender systems, how previous works used them for regularization and how we are going to use it for prediction and which one is better. The goal of our approach is to predict the unknown ratings. Let's say we have m users and n items. Then we have access to this rating matrix where some of the ratings of the users on items is known. But as you can see, more than 95% or 99% of them are unknown. And the goal is to predict these unknown ratings. We focus on hybrid recommender systems, where all the information about users and items, such as ratings and content information, are used for predicting the ratings. The most widely used neural network structure in literature is denoising autoencoders. You see a list of papers here. I'm going to show you that these methods use neural representations as regularizer. Here is the structure of the previous works. There are two autoencoders, one here for the users and one for the items. The user autoencoder reconstructs the user information, ratings and side information, and the output of the middle layer is user neural representations here. The output of the middle layer of this autoencoder is item neural representations. As you can see, these representations are not used for prediction. There is a second set of representations, U and V, achieved by matrix factorization of the ratings, and these U and V are responsible for predicting the ratings. But it is well known that matrix factorization is overfits easily. So to prevent overfitting, the previous works try to keep U close to the user neural representations and keep V close to the item neural representation. Here is the general format of the objective function of the previous works. They have these two reconstruction terms to reconstruct user and item rating and side information. They have the matrix factorization term to predict the rating, and they have the regularization term. U should be close to user neural representation and V should be close to the item neural representation. You can see that there are two hyperparameters here. So what's the issue? What are the issues of this approach? First, it's difficult to set lambda 2 and lambda 3. It needs a lot of works, the hyperparameter tuning. Second, they have U and V and the network parameters, so they have a difficult optimization. Third, they train a network, which is a difficult task, but they don't use it directly for prediction. That's why we propose our approach, no representation as the predictor, or NRP. So the goal here is you can see this is our objective function. So we have removed the U and V, the matrix factorization terms. We use no representations for the prediction task directly, and we also have the reconstruction terms. Advantages are that we remove the hyperparameters, our training faster, our method has less number of parameters, and we'll show later that it achieves better results too. We also propose a direct structure, no representation with a direct structure, where we remove the decoders, which saves 50% of memory and leads to faster optimization. We also replace dot product with multilayer perceptron, which improves the power of our approach. We report results on 4 datasets. The smallest one is movie-length 100K and the largest one is Ichiban. We also report results on, we report RMSE, the smaller the better, and precision, the higher the better. Here, we report RMSE precision, number of parameters, and training time per epoch of different methods on movie-length 100K and movie-length 1M. DHA and ASDAE are the previous autoencoder-based methods that use neural representation for regularization. NRP-DHA and NRP-ASDAE are our method. They use the same structure as DHA and ASDAE, but they use the neural representations for prediction. We can see that using our approach, we can decrease RMSE, improve precision, we have less number of parameters, and better training time. Our direct approach also achieves the best results, least number of parameters, and least training time. We also compared our method with several state-of-the-art methods, and we showed that our approach achieves the best results. The conclusion is that it's better to use neural representations for prediction, and by removing the decoders, replacing dot product with multilayer perceptron, we can achieve even better results. Thank you.